Hi, everyone. My name is Derek Davis from the University of Rhode Island. I'm excited to welcome you to the final in our series of webinars detailing the results from the fourth LIGO Virgo Kagra gravitational wave transient catalog. Today's webinar is going to be focusing on investigations of lensing signatures used in events from this catalog. I'd now like to then introduce the host of today's webinar, Justin Jancourt from the University of Louvain.
Hello, everyone. Welcome to this webinar. As Eric just said, we're going to cover the searches for gravitational wave lensing in GWTC-4. Before getting there, let me first say that this is the last seminar in the GWTC 4.0 series. So for those that have joined the others, thank you for your attendance, and also thank you for being here today. And with that, let me also introduce your speakers for today. So there will be myself. There will also be Ankur from ICTS in India, Among Seo from University of Glasgow, Anya Liu from University of Illinois, and Rupreta from the Inter-University Center for Astronomy and Astrophysics. As you will see, all of us will give you different aspects of the paper. Together with the speakers, there will also be a panelist to answer your other questions, which is composed of Ajit also from ICTS, Alvin from the University of Tokyo, Jose from the University of Copenhagen, and Mick Wright from Utrecht University. So now that everyone's introduced, you will see everyone throughout the webinar. Let's dig into the topic of today. To start with, let's go to a quick introduction to gravitational wave lensing, or to gravitational lensing in the first place. Most of you may be familiar with this effect with light. So as described by general relativity, if you have a massive object in the path of a wave, it's deflected. And that's basically what we know as gravitational wave lensing, and it's really well known for light and is also commonly used in astronomy. So you may have seen some of these images. For example, here when your alignment is good between your source and your lens, you have a nice Einstein ring that appears. Or when your alignment is a bit less good, you can get several images with sort of Einstein cross, it's called. Or when you're not in a regime where you get multiple images, you can get something slightly different where you have this sort of magnifications and extra distortion effects. Now, this is what is the most commonly known with light, but here we're there to talk about gravitational waves. So because gravitational waves are different from light, have different wavelengths, but also we observe them differently, so they're transient. We also have different detection methodologies, and we will also see different effects in our gravitational wave detectors. So we basically distinguish two regimes depending on whether we have a massive lens or not. And also, yeah, we then see different things. So for example, we have the geometric optics where we have a massive lens, typically a galaxy or higher mass. In that case, your gravitational wave is deflected by the galaxy and it splits in several images, which have the same time frequency evolution, but they can have an overall magnification, which means that their amplitude will be larger, for example. They will have a certain time delay, where time delay depends on the characteristics of the galaxy. And they can undergo an overall phase shift. Conversely, if you're in a wave optics regime, so you would have smaller lenses, so more compact objects. Let's think about isolated black holes or stars in field of stars. In that case, you don't have your wavelet split in several images, but you keep a single image which undergoes a frequency-dependent beating pattern. So your final signal, as you can sort of see here, is not a simple, let's say, gravitational wave, but you really see that the whole time frequency evolution is affected. So this is the kind of phenomenon that we'll be looking for in the data in the paper that we're presenting to you today. Now, before going there, it's also important to see why we're looking for this gravitational wave lensing. Well, first of all, it's a prediction from GR, so that's already nice on its own, and it's a prediction of GR that's expected to be seen with a reasonable rate. So based on current forecasts, we expect to see about one lens gravitational wave for 1,000 unlensed gravitational wave detected. So it depends, the exact relative rates you can see on this figure depends on the redshift horizon, but nowadays we're about here. So you see that it's indeed about 1 in 1,000 if you're not too stringent on the magnification. So that means that we really expect to see this as we see more and more gravitational waves. Finally, a bit like in astronomy, if we start seeing lens gravitational wave, we can also use the detections and the observation of these lens gravitational waves to study new avenues. In particular, there would be new avenues in astrophysics, cosmology, and fundamental physics, with, for just to give some examples, improved tests of general relativity, the localization of merging black holes, precision cosmology, study of dark matter and of microlens populations. So it also opens a lot of new avenues, which is what would be a milestone to detect such lens gravitational waves. So now the scene is set. What we'll be talking about related to these gravitational waves for this webinar will be the searches for these strongly lensed image pairs, searches for single distorted signals, as they have been presented before. Then, as you will see, there will be a deeper dive in a particular event that presents some peculiar characteristics. And then we will go into the implications of our results, giving more insights on lensing statistics and lensing rates before concluding the seminar and answering your questions. So just to then dig into the data and what we're looking at exactly here, we will consider all the newly detected black holes found in GWTC-4, which have a false alarm rate that's below 1 per year and that have an astrophysical probability higher than 50%. So in total, that means that here we consider 84 newly detected binary black holes. So they're basically the ones that have been detected between the end of this O3b here and the end of O4a here, so in the red hatched region. So they come on top of this catalog. You also see here some, let's say, insight on the characteristics of these newly detected events. We've highlighted some particular events that have peculiar characteristics compared to the others. Throughout this presentation, when we talk about unlensed sample or unlensed analysis, this refers to the vanilla analyses that are presented in GWTC4. So when we use unlensed samples, for example, it means that we use the samples and the results that are presented in the catalog, which you have seen in the paper or in the past webinar. And the main waveform that we use is IMR phenom XPHM spin Taylor, unless we specify otherwise, which may happen, as you will see later. Finally, in terms of strain, all the strain data that is being considered here is exactly the same as the one that's used for the GWTC 4.0 catalog, so also including glitch mitigation strategies, for example. And then finally, a last tool that's important to understand, to interpret results and to follow throughout this presentation is the so-called unlensed background. So when we look for lensing to interpret the significance of our statistic, we rely on an unlensed background. The idea is to have a population or a mock population of unlensed signals, which we then analyze both under the lensed and unlensed condition to see how much our statistic can fluctuate due to the noise. And so for this O4A analysis, we make such a background by having 254 events that are generated. Their masses and spin follow the most up-to-date results prior to observation. So they follow the power law plus peak distribution from GWTC3 and the spin distributions found in GWTC3. We do all injections and recovery with the IMR phenom XPHM spin Taylor waveform. To also have the effect of realistic noise, we use real stretches of O4 data that are devoid of signals. So we look for places where there's no signal and use this noise as noise for doing the injections. And as a proxy to detection, we consider signals that have a network SNR higher than 8. And so here on the figures, you see the two left ones that represent the mass characteristics or how the masses are distributed for our events. And on the right-hand side, you see information related to our spins. So this is expected to represent our best knowledge of the astrophysical black hole mass and spin distribution prior to observation for GWTC4. With that, now that the scene is set, that you know the data we're looking at and the tools we're using, I will pass the word to Ankur to give you the update on the results for strong lensing.
Thanks, Justin. So now let's start looking at the searches for multiple lensed images. This, as Justin said, are multiple copies of the same signal, possibly caused by a massive object like a galaxy or a galaxy cluster. So first we search among superthreshold pairs, that is, pairs of signals among those that have already been identified by the catalog team as most likely to be real signals. There were 84 such signals, which is about 3,500 pairs. So to reduce the computational burden of analyzing all of these pairs, we use a hierarchical approach to systematically veto obviously unlensed pairs. So there is a tier 1 consisting of 2 pipelines, which identifies those which are obviously not copies of each other. So this could be because, let's say one of them is a 10-10 solar mass binary, while other is a 100-100 solar mass binary. They are definitely not copies of each other. Or maybe they have no sky overlap, or maybe their phases measured at different detectors at some frequency are not consistent with each other. So such tier 1 pipelines reduce the total number of pairs from about 3,500 to 105, which are then passed on to tier 2, which jointly analyzes jointly analyzes each of these pairs to check whether they are consistent with the lensing hypothesis. This further reduces the pairs by a factor of 2. And the final set of 50 pairs is passed to the Hanabi pipeline, the tier 3, to compute the actual final base factor with population information as well as selection effects. Next slide, please. So on the left, we show how the very first cut is done. So this is conservative. Since these two pipelines return different statistics, we first bring them to a common baseline by using the background Justin talked about 2 slides ago. We compute the false positive probability per pair for each pair using the statistic returned by the pipeline. And we put a threshold of 1% to be considered as potentially interesting. And we choose a conservative way of taking a union of the pairs which are passed by both the pipelines in tier 1. Once these pass to tier 2 and finally to tier 3, we obtain a base factor, which is shown for the final set of 50 pairs on the right. So it is important to notice that the base factor increases towards the left. So the 3 pairs, which are highlighted in green circles, are the most significant. However, the actual base factor of these pairs is still below 0. So we conclude that even after checking over 3 different pairs and taking into consideration that not all of them have the same probability of astrophysical origin, the net result is that we find no strong evidence of multiple images among super-threshold pairs. Next slide, please. Yes. So next we search for this possibility that since multiple images are generated by these lenses, not all of them could be detectable. It could be that one of the images is super threshold, that we detect it with confidence, while the other may be buried in the noise. So we search for sub-threshold counterparts to super threshold events. This is done using a targeted search using PyCBC pipeline. Search templates are obtained from the posterior samples of super threshold events, and we then select triggers based on a single template FAR, and an additional constraint that the subthreshold image has to have some non-zero overlap with the target event. With this cut, we find 177 triggers with FAR less than 1 per month, of which 20 are with FAR less than 1 per year. The top 2 candidates we find are not present in the extended GWTC candidate list. They are listed below in the table. However, when we follow them up with the tier 2 pipelines, tier 1 pipelines, they are vetoed as being not interesting. So to conclude, we do not find any strong evidence for sub-threshold counterparts as well. Next, I will hand it over to Engwang for discussing the search for single distorted signals.
Thank you, Ankur. So now let's take a look at the result of our search for single distorted lens signals. First, we search it for type 2 images of GWT signals. A type 2 image arises when the signal passes through a saddle point in the lens potential, introducing a constant phase shift of pi/2 across all frequencies. Type 2 images are expected to be rare in current detections. The strong lensing is intrinsically uncommon, and even when it occurs, not all images are detectable with sufficient signal-to-noise ratio, but they are important because a confirmed type 2 image would provide unambiguous evidence of strong lensing, and if we do not explicitly search for them, and these signals could be misinterpreted as deviations from the general activity, since they can mimic the beyond GR effects. For this search, we analyzed events using the Golden pipeline. and the pipeline produces two base factors for each event. So one comparing the type 2 versus type 1, and the other comparing type 2 versus type 3. And also, since type 1 and type 3 images are not distinguishable in practice, we take the mean of these two base factors as our statistics. And we also compute the same base factors for the lensed background introduced earlier and compare them with those from the observed binary black hole events. As shown in the figure, we do not find any significant outliers, meaning that there is no strong evidence for type 2 images. Next, we search for microlens signals, assuming a point mass lens model. We restrict the point mass model because within the detector's sensitive frequency band, the microlens candidates are well described by the point mass model. The model introduces two additional lens parameters, the Redshift lens mass and the dimensionless impact parameter. These are included in addition to the 15 standard CVC parameters in the Bayesian inference. So for the priors of lens parameters, we assumed a uniform prior on the Redshift lens mass between the 1 and 10 to the 4 solar masses, and a parallel prior with index alpha is equal to 1. So basically the log uniform for the dimensionless impact parameter, and the range is between the 0.01 and 3.0. And we adopt the Grapelim's pipeline to analyze the signals under the point mass lens model and to compute base factors. So here, the base factor is defined as the evidence ratio between the point mass microlensing hypothesis and the lensed hypothesis. Again, we compare the base factor distribution from the observed binary black hole events with that from the lensed background. And as shown in the figure, we do not find any significant outliers except for the GW23-1123. This event has the highest base factor measures to date. And to assess its statistical significance, we compute the false positive probability. So it is defined as the fraction of background events with a higher base factor than this event. In our case, the no background events exceeds the base factor value of the event. So we place an upper bound of 1 over the number of background events plus 1, so the 255, or about the 0.39%. And we also evaluate the global p-value, which accounts for the trials factor or the look elsewhere effect. So we test multiple events rather than just one, so the probability of finding significant outliers by chance increases, and this is accounted for in this global p-value. So here the trials factor corresponds to the number of events we analyze, so the 84, and we obtain a value of 28%. And it's not statistically significant. In other words, it's too high. So this is mainly due to the limited number of background injections. And another point to keep in mind is the low abundance of GW23-1123-like events. So these events exhibit a non-negligible effective processing spin, and such events are rare in our background. So this increases the risk of false alarms due to degeneracies between spin and lensing. And also the signal has a short duration, so it might be more susceptible to non-Gaussian features like glitch, which can mimic the lensing signatures. So further investigation is needed to quantify the impact of these effects. So I will now hand it over to Anya for more details on this event in the next slides. Thank you.
Thank you. So as Emil already showed on the previous slide, GW23-1123 stands out with a high base factor compared to the rest of the events. But beyond that, it's also unusual from an astrophysical perspective. First, let's look at the detector frame chirp mass shown in the figure. And from the horizontal axis, you can see that the chirp mass is extremely high. This is a very massive binary. In fact, it's the most massive binary black hole detected so far. But there is something else interesting here. If you compare the different colored curves, which correspond to analysis without lensing, using different waveform models, you can see noticeable discrepancies between the waveform models. In particular, the blue curve prefers significantly higher chirp masses than the others. This level of disagreement already hints that something unusual is happening, and it complicates the interpretation of this signal. Moving on to the next slide, we present the component spins. What immediately stands out from this plot is that they are extremely large. The posteriors cluster near the upper bound, approaching values close to 1. So taken together, this is a very unusual event. It's the most massive binary black hole observed so far, with spins that are pushing to the astrophysical limits and high base factor compared to the rest of the events. This naturally raises the question, is this really an extreme astrophysical system, or are we missing something in our interpretation or modeling? And could lensing provide some hints for the explanation? To investigate this further, we look at the waveform reconstruction. In the main panel, the light gray lines show the whitened data from the LIGO Hanford and LIGO Livingston detectors. The red curve is a model-agnostic reconstruction, capturing coherent power across the two detectors. The blue curve shows the unlensed reconstruction, while the purple curve shows the lensed waveform. It's hard to judge by eye which model matches the data better from this figure alone, so on the right, we show the mismatch. The lower mismatch values indicate better agreement with the agnostic reconstruction. And here you can see that the lensed waveform consistently achieves a lower mismatch, suggesting a better match to the data. So we then repeat the analysis, including lensing, with a point mass lens model. Here we show the detector frame mass again, detector frame chirp mass, now including the point mass lens results shown as filled colored contours. There are three main observations from this plot. First, the disagreement between waveform models is reduced. The lens results show better consistency between each other. Secondly, the posteriors shift towards lower chirp mass values, particularly for the blue curve, moving into regions where waveform models are more reliable. And third, the lens posteriors are broader, reflecting the additional freedom introduced by the lensing model. Finally, let's look at the spins again. Here, the lens results are shown in green lines. We now see much more support for moderate spin values, which are more typical astrophysically. However, we should be cautious. From previous studies, we know that lensing is degenerate with spin-induced precession. So it remains unclear whether the previously inferred extreme spins were due to unmodeled effects or whether the signal truly contains strong precession. At this stage, it is difficult to distinguish between these two possibilities. Next, we compare the evidence for lensing more directly, and here we show the base factors between the point mass lens analysis and the unlensed models for the same three waveform models as before, the IMR Phenom XBHM, the NR surrogate model, and IMR Phenom XO4A. They are shown in the same colors as before from the plots. In general, higher base factors indicate stronger support for lensing, and here we quote the log 10 values. What you can see is that the first waveform model shows very strong support for lensing with a base factor of around 10 to the power 3.8. For the second model, the support decreases. There's still support for lensing, but weaker. And for the third model, we find very mild preference for lensing. This trend mirrors what we saw earlier in the mass posteriors, where the waveform models disagreed. That likely reflects the extreme parameter space of this event, where waveform models are less well calibrated and therefore they are less reliable. Since these analyses assume a point mass lens, we can also infer the lens properties, the redshifted lens mass, and the impact parameter. Here we show the results for the two models that favor lensing most strongly, the IMR Phenom XBHM and the NR surrogate, and both suggest a lens mass of roughly 800 to 900 solar masses with the uncertainty ranges shown in the table. The impact parameter is constrained to be around 0.6 to 0.7. In principle, this would allow us to infer the nature of the lensing object. However, there is an important caveat. Astrophysical lenses are rarely isolated. a point mass lens could be embedded within a larger structure, such as a galaxy, which would introduce additional macro magnification to the overall signal. If only one macro lens strongly lensed image is observed, we cannot disentangle this effect without detecting a counterpart image. So the results shown before assume an isolated point mass lens, which may be an oversimplified scenario. This means we should be cautious when interpreting the astrophysical implications. With this in mind, we also searched for signatures of strong lensing. We looked for type 2 images using different waveform models, different detector configurations, and priors. But overall, we found no consistent evidence for a type 2 image. We also searched for lensing near-fault caustics. Here again, the waveform models disagree, and the results are not significant enough to claim strong evidence of fault caustics lensing. Finally, we tested whether the apparent lensing signal could instead be caused by unmodeled noise features. One possibility is non-Gaussian noise or glitches. We performed the analysis using clean data with glitches removed, and the signal remains coherent between Hanford and Livingstone detectors. This makes a glitch explanation unlikely, since independent glitches would not produce consistent features in both detectors. Another concern is contamination from narrow spectral lines, such as the 60 Hz power line. On the right, we show the spectrograms for the lensed and unlensed reconstructions. And the differences between these two are spread across multiple time frequency bands rather than localized at a single frequency. This indicates that the effect is broadband and not driven by a single spectral line. So to summarize, this event shows intriguing structure consistent with possible gravitational lensing. However, there is a strong degeneracy with other effects. The waveform systematics further complicates the interpretation, with different models given different levels of support. So as a result, this does not make a decisive evidence for lensing. That said, this is a new and very exciting signal. It's the most massive binary black hole observed so far, with the highest base factor found. And while this single event is not sufficient to claim strong evidence for lensing, future detections and population-level studies may provide a much clearer astrophysical picture. And with that, I'll hand over to Anupreta.
Thanks, Anya. So I'm going to talk about the implications. First, I'll start with the lensing rate predictions. Based on the latest models we have for the binary black hole population, we make predictions for the rate of strong lensing expected in the data from the O4A observing run. So firstly, we compute these numbers for the two kinds of lenses. One, where the foreground lensing effect is produced by individual galaxies, and second, the case where the lensing effect is produced by clusters of galaxies. Now, since the choice of the redshift-dependent merger rate density model is an important ingredient in this calculation, we compute these rates for two types of models, which are currently preferred in the collaboration, and it's shown by the two rows in the table. Lastly, we apply a threshold on the network SNR to ensure that the lensed events are detectable. So the column RD means both the brighter and the fainter lensed events meet the SNR threshold, and the column RS means that just the brighter event meets the SNR threshold. So taking all of these different models and the lensing probability calculations, we compute these lensing rates, and what we find is that at galaxy scales, 1 in order of 1,000 events could be lensed, and at the cluster scales, 1 in order 10,000 events could be lensed. These predictions are consistent with the current results of no confident detections of strong lenses so far. So in the next slide, here we talk about the constraints on the merger rate density models. So in the previous slide, the kind of analysis we did was forward modeling, and here we are turning the problem around. by looking at our observed data and the results obtained from the lens searches. And what we do is that we instead put constraints on the underlying models for the redshift-dependent merger rate density. So currently, we are making no strong claims for the detection of strong lensing. So what we do is we start with all of the R of Z models that are consistent with the latest sample of confirmed gravitational wave events, which are shown in the gray shaded region. We check to see if that these models are correct, then how many strong lenses we should have detected. We find that all of the models shown with the green hatched region are allowed as they are consistent with the non-detection of strongly lensed gravitational wave events. For reference, we also show similar results from the non-detection of the stochastic gravitational wave background from another working group in the collaboration. In the near future, when we begin to have confident detections of strongly lensed events, we will be able to put more stringent constraints on these merger density models. That's all from me. So I will hand over to Justin to present conclusions of this work.
Thank you. To give a brief summary of the different points that we have shown here based on the GWTC 4.0 data, on the pairwise searches, all our superthreshold pairs have a bias factor compatible with the unlensed hypothesis. We also did not find any subthreshold counterparts to one of these superthreshold events that would favor lensing. Finally, on the single distorted signal searches, no evidence for type 2 images. And then for the point mass wave optics analyses, with the exception of GWTC-4.0, we have found no signals that have significant signatures. Regarding GWTC-4.0 itself, we constrain its false alarm probability with a restricted background. However, we know that the interpretation is complicated due to the limited number of event cycles that we have in band, the waveform systematics, also the rarity of this event. And so we know that this is an extremely exciting event on different fronts. And that to learn more about its nature, probably we'll need to have more observations in the future. So it's a good reason to stay tuned. And finally, we look into the implication of the non-detection of strong lensing, where basically we've seen that the rates now gives us a lens versus unlensed detection rate of the order of 10⁻3, which is compatible with most predictions. And we're also able to independently place constraint on the merger rate density at high redshifts, independently from the stochastic gravitational wave background, for example, but also in line with this other method to put constraint. With that, we'd like to thank you for your attention, and we welcome questions. Feel free to type those in the chat, and we will assign them to the panelists and the speakers and answer your question the best way we can. Thank you again for attendance. Okay, I see the first question coming. I will pass this question to Ajit. So the question is, would a BBH merger embedded in AGN accretion disk count as a lens gravitational wave event if it happens behind a supermassive black hole along the line of sight? And if so, what kind of signature would such events have? Ajit, you're muted.
Yes, yes, thank you. This is an interesting astrophysical possibility. We could think of it. So this is, of course, we don't know the astrophysical uncertainty of these things. However, if the central black hole is of supermassive masses, which is more than 1 million solar mass to 1 billion solar mass, then typically the gravitational length scale of the black hole is actually still larger than the wavelength of the gravitational waves that would that we observe in LIGO, Virgo, Kagra. So that sort of a lens is unlikely to introduce the kind of wave optics effects that we suspect in this particular event that we have seen. However, it could produce a strong lensed event. So that would appear as basically multiple images separated by a small time delays of less than a fraction of a second. That is indeed a possibility, but yeah, that is something exciting possibility that we should look for in the future.
Thank you for your answer. Are there any other questions? Okay, I see that there's another question related to optical follow-up for GW231123. Let me pass that one to Mick.
So whether if is an optical follow-up possible? In short, the answer is probably not. So in the case of GW231123, of course, this is a binary black hole. There's no suggestion of a neutron star, so an electromagnetic counterpart to the event is not supremely likely. And in terms of the host galaxy identification, this would be, if you were to assume it was actually indeed lensed, this would be quite complicated to untangle since you would need to identify first the correct lensing model and then run back through and only then could you start the process of galaxy identification and then check for lensing there. And there's no guarantee that the actual galactic signal that you would get would be lensed in the same way. So unfortunately, the answer is most likely not.
Thank you. Have people in the audience any other questions? Okay. I'm giving it a few more seconds in case anyone wants to answer or ask one more questions. But if not, then I think we're nearing to the end of the webinar. Okay, then I guess that means that the presentation was clear and everyone's happy with what was said. Let me thank everyone again for the attendance, also the speakers and the panelists for their participation. And I wish you all a good rest of the day. Bye-bye.